Okay, welcome back to Math 365, partial differential equations. It's so nice to see you. So today we're really continuing our discussion of the wave equation, but we want to do it with a little bit more of a physical lens. So in particular, we want to introduce this classic separation of variables technique and some consequences. So the question we're basically trying to answer is, how do you find the fundamental tone of a string, right? And then how do you find like the other, what do you call them, the overtones? So how do you find these fundamental frequencies of the string when we're playing the musical instrument? And we've already characterized all solutions to the 1D wave equation. They're completely characterized by their initial conditions, but you would be hard pressed to, kind of cook up the initial conditions that give you a pure tone solution just off the top of your head. You might be able to, I don't know, but the technique that I'm presenting is the one that kind of classically came through, and it starts with this idea of simply saying, like, I'm going to try to switch to Tx. The reference we use most often uses T variable first. So you take this function, which is now you're thinking of the one-dimensional wave equation on a string with the endpoints held fixed. And so this being the displacement, and now suppose that this is equal to like a product of two functions, say v and phi. And for the moment, we'll take c equals 1 just to sort of focus on the mathematical characteristics. And we'll look at this inhomogeneous wave equation. There's not going to be like external forces on the string as we're plucking it, trying to find those fundamental frequencies. And so it's kind of interesting to me that this is where separation of variables comes from, right? The variables are separated across two functions. And it's kind of interesting to me that this physical form kind of gives you for free so much information that we'll see throughout the class. What's it kind of saying? That, you know, as you move through space-time, you go to any particular time slice, and on that slice, you've got this, you know, particular scalar that affects your amplitude, which is fine. I mean, it's just interesting to me that simplification automatically gives you this good physical model. But I guess sometimes a simplification is what you need, you know, to model kind of like this simpler process of like bowing a string or plucking the string or something. But, you know, maybe at a later time I'll have some more to say about that, think about it some more. But the thing that we're going to look at is, so let's use our usual assumptions. So u is a C2 function. Let's say that there is some open set on space-time where u is strictly positive, because I want to be able to divide by u. And on that open set, we have the following, you know, separation of variables theorem. So this equation, with this having that form, I can say that there is some constant k with the following. So I'll write these as partial derivatives, even though that's not quite accurate. So v is a function of one variable. So this is like v double prime. Well, maybe I'll kind of be honest. So this is sort of like the analog of partial derivative with respect to t, but it turns into v double prime equals k times v, and separately we get phi double prime coming from the partial derivatives with respect to x equals k times phi. And this is quite easy to get through direct calculation. So let's see it. If I just directly substitute v times phi into this equation, so then you can see that what I'll get is direct substitution gives me what? The partial derivatives hold x constant, so I end up with v double prime times phi minus, and now partial with respect to x will hold v constant and give me v double prime equals 0. The reason why you like this setup, of course, now is that you're heading towards turning this into a couple of ODEs, which is going to allow us to use that knowledge to then find some of these solutions. So now dividing through by u, since you know it's not equal to 0. So the next step is valid whenever it's true that u is bigger than 0. So let's just sort of keep that in mind. But dividing through times v phi is now going to give us, and bring this to the other side, is now going to give us v double prime over v equals phi double prime over phi. So you get this nice symmetry. So here comes the argument now. The argument is that now you've got a function of t. Like maybe I've done a disservice by suppressing the variables. Here's a function of t only, and here's a function of x only. And so what does that mean? It means when you change x, the left-hand side does not change, right? So think about taking x equals 0 or x equals 1/2 or 1/3 or 1. Pick x whatever you want. It still has to be equal to this left-hand side. So this has to be a constant. So this has to be a constant. But also you can change t. But this also can't change, because if it did, like, this wouldn't be constant, right? So because you've got one function of t equal to another function of x, like if you've got f of t equals g of x, where t and x are really independent of each other, then really this means that f has to be equal to g, has to be equal to some constant. That's the only way that you can have such a relationship hold good for every single t for every single x. And so that's exactly what we're doing. So we're just saying, like, let's call this constant k, and then we're arriving at these two, what you might call eigenvalue equations. So v double prime equals k times v, and phi double prime equals k times phi. I did call these eigenvalue equations, and it's really true, right? So think about the collection of all smooth functions on the real line, for instance. So smooth function means that that it's infinitely differentiable. You can differentiate it as finitely many times as you want, and it's still infinitely, differentiable. You can think of the operator that, you can think of L of f is equal to f double prime. This is an operator from smooth functions to smooth functions. It is a linear operator. You remember the definition of eigenvalue and eigenvector from linear algebra. It says that when you plug in a vector, right, you've got a linear operator on a vector space. when you plug in a vector, if you get a scalar times that vector as your output, then f is an eigenvector and k is an eigenvalue. And so that's why these are called eigenvalue equations. They're, or, you might even call these eigenfunctions, just to respect the fact that you're looking at a vector space of functions. Okay, fine. And so we've learned that we're kind of interested in this eigenvalue equation. And just for reasons of convenience, we usually take lambda bigger than 0 and write k equals minus lambda. In the hypotheses that are physically reasonable for us, this constant will be negative. I'll speak to that a little bit later, but if you want a positive constant, you can just do this little device, and then you end up with this equation, something like minus phi double prime equals lambda, the lambda phi. So this now matches the notation in your book, and this is the one-dimensional Helmholtz equation. So whenever someone says Helmholtz equation, they're talking about the eigenvalue problem. But it's a little bit more general. I won't do the higher dimensional case today, but you could, the more general wave equation with C equals 1 is this, right? Laplacian being 2 partials with respect to x plus 2 partials with respect to z plus 2 partials, or plus 2 partials with respect to y plus 2 partials with respect to z, so on and so forth. So you keep on adding more terms like that. And if you do the argument that I just did, with u times v, you end up with still this equation, but this one now kind of becomes replaced with negative Laplacian u equals, or negative Laplacian phi equals lambda times phi. And this is the one that's properly called Helmholtz equation. Which first one? If you redo this argument with this equation instead of that one, you'll get this equation instead of this one. Right? And in fact, in one dimension, the Laplacian is, 2 space derivatives, which is like phi double prime. And this is actually pretty hard to solve. It's like, like in a graduate course on PDE, you could solve this for lots of different domains. For us, I'll be able to show you at least how to do it on a square domain, or how to do it on the pizza slice polar coordinates domain, sort of the polar coordinates version of a square domain. That's coming in later sections, but for now, let's focus on the vibrating string problem. And the vibrating string problem comes with certain built-in hypotheses, right? You've got a string going from 0 to L with with the endpoints having to be fixed, right? So u of t0 equals u of t L equals 0, for instance, right? And so you can put this 0 initial condition on either one of these that you want, but I think it quite makes sense to take phi of 0 equals 0 and phi of L equals L. So like initial conditions having to do with the spatial part being put on like the spatial function, and that also makes sense to me in that if you decided that v of 0 was equal to 0, then you are perhaps affecting your other initial condition that has to do with use of t, which might be a problem. So it's standard to write this initial condition in terms of space variable or space function only when you're separating the variables. And so then you've got this set of initial conditions with this equation. B0, of course. Yeah, thank you. And so you've got this eigenvalue problem with this set of initial conditions. And so you're asking yourself, a linear algebra question, which is what are the eigenvalues and eigenvectors of this setup? Of course, you know that eigenvectors can't be 0, like eigenvalues can, but not eigenvectors. So we're looking for non-zero solutions to this equation satisfying those initial conditions. And so this is an ODE problem. This is an ODE problem. And for the most part, I'm just going to let you read up on the way that you solve constant coefficient ODE. But I can do what? Well, I'll give a little bit of an overview. So I rewrite this as phi double prime plus lambda times phi equals 0. And like the way you try to approach this in ODE is you kind of use this little trick that, you know, probably it's due to Leonard Euler like everything else, but I don't know who it came from initially, but you do something like you search for a solution of the form e to the RT. Why would you possibly search for a solution like that? Like if you stare at this problem long enough, it starts to make sense because these are the functions where if you plug that in, what happens? You get r squared plus lambda. You get something like r squared plus lambda times like phi double prime plus times e to the RT or something like that equals 0. And then you end up searching for an R that solves r squared plus lambda equals 0. And so this is called the characteristic equation of the ODE. And so what you want to do is sort of solve that characteristic equation. And so you're going to get that R is now equal to plus or minus I times the square root of lambda, right? Well, and then you're ending up with your solutions are like you know, e to the r times t times a constant plus like e to the minus r times t times a constant. Although I should back up a little bit because two things, complex numbers kind of appeared. I'll talk about that in a moment. And the second thing, this was under the assumption, of course, that lambda was bigger than 0. I did say that, but I didn't, you know, I just said it, right? Is it actually true? So maybe we can investigate that a little bit. If you take this equation, say that you've solved this equation, and solving a second order ODE, you know it's quite convenient to use complex valued solutions so that you can use like, you know, e to the IT. So let's say that we've solved this and that we've taken a complex valued solution. We can always rearrange it later on to make it go back to real valued for plugging in. But let us multiply both sides of the equation by phi bar. Or even if you don't want to do complex solution, like even if you just have a real solution, we should still be able to do some work. So let me show it to you. So let's multiply both sides by phi and then integrate from 0 to L. So let's take this to be equal to lambda times phi squared dx. Or if you allow complex solution, multiply both sides by the conjugate of phi by phi bar, and you'll end up with sort of the norm squared on this side and phi bar there. But I won't sort of write that out, maybe for like psychological reasons. And for this, I want to do an integration by parts. So actually, I'll leave that for class exercise, take 30 seconds. Integration by parts, respect the boundary conditions. What do you get? So integration by parts is what? It's like the integral version of the chain rule. I like to think of it as you can move one of these derivatives to the other term, right? And you have to pay for that by including a negative sign and also by including some boundary term, right? So your boundary term would be like phi prime times phi evaluated from 0 to L, but in this case, your boundary values are 0. So the boundary term zeroes out. So you get phi prime times phi prime. If this was like phi bar, you'd have phi prime times phi bar prime. So in the complex case, you would end up with that. In the real case that I'm illustrating, you'd end up with just phi prime squared. Either way, arriving at the same conclusion. And this is kind of nice because I've got integrals of squares. Integrals of squares can't be negative. So first of all, I want to use the fact that phi can't be 0, right? Phi can't be the 0 function. And since it's continuous, this integral can't be 0. If you're integrating a function that's non-negative and continuous and not everywhere 0, its integral is going to be strictly positive. We've spoken about that before, but basically if you have some point where you're positive, by continuity, you must have a whole region where you're positive. Integrating over that region makes you bigger than 0. So dividing both sides by this integral, you can now see that lambda is bigger than or equal to 0. Yeah, the comment was you can also think of it physically. Sure, this is a mathematical demonstration of the fact. Yeah. Yeah. And so what about, could this be 0? Could lambda be 0? So what would happen then? So if lambda were 0, then what happens? This side of the equation has to be 0. And once again, by the same argument I said before, like sort of like the contrapositive of that argument, if you've got a function that's non-negative and continuous, and you're integrating that function in this closed interval, and that integral is equal to 0, then this implies that, yeah, the function has to be 0 everywhere, because again, like contrapositively, if the function weren't 0 everywhere, the integral couldn't be 0. So yeah, it tells you phi prime is 0, and therefore phi equals c. Well, it tells you that like this part would have to be constant. But which constant is it? Remember, your boundary values are telling you that you have to be 0 on the boundary. So it would have to be 0 due to the boundary conditions. But again, eigenfunctions can't be 0. Otherwise, by definition, they're not eigenfunctions. And so therefore, it must be true that lambda is positive. Why do you care about that? Because again, when you go back to solve this ODE, you write down the characteristic equation. It matters whether that's positive because if negative lambda were positive, you could just take the square root. But if you knew that lambda is positive, which we now know, square root of negative lambda giving you plus or minus I times root lambda. So everything's completely justified now. There's like 3 different sort of cases depending on whether the discriminant of the characteristic polynomial of an ODE is like positive 0 or negative, right? And we're here in the case where that's negative, which is the case that gives us sines and cosines. And so this is now telling us from ODE theory that phi of x, well, you can write it as a linear combination of these complex exponentials, but you know, if you want to convert that to a real valued solution, that's going to be some constant times cosine of root lambda times x plus some constant times sine of root lambda times x. E to the I theta is like cosine plus I times sine, and you know, messing around with the linear combinations, you and like if you want real solutions, then you take A and B to be real. If you want complex solutions, there's you can take A and B to be complex, but then why not just do this? So both of these things are true, but perhaps with different constants. But I want to focus on this one. And I want to appeal again to our boundary values. So one of those constants is 0. Which one is it? What do you think? Right, the answer was A. And the reason why, of course, is that cosine of 0 equals 1, which is rather inconsistent with the initial conditions. So the general form of the solution is constant times sine of lambda x. And so if you like root lambda x, thank you. So if you like, sine of root lambda times x is like a basis for the space of solutions to that equation that satisfies the initial conditions. And so what about the other boundary condition? So we'll speak more about solving this equation in a minute. For now, I'm just focused on this particular piece. Phi of L should also be 0. So that's true. So like, what about that? Let's figure it out. Yeah, the question is, what about phi of L also being equal to 0? I mean, this also puts a constraint on lambda, doesn't it? Because if I have 0 equals phi of L equals, let's take b equals 1, doesn't really make a difference. So x is equal to L, of course. So root lambda times L, yeah, should be some multiple of pi. Thank you. So you know that sine is 0 at 0, at pi, at 2 pi, 3 pi, so on and so forth. This gives you an equation for lambda. So as promised, it's like a positive number. And so, and actually it can depend on n. So let us now start calling it lambda n. So you're right, lambda n is now pi squared, n squared, over L. Over L squared, thank you. Almost. We're not quite there, but it's very much related. Yeah. Certainly characterizes the harmonics of the string. So what this shows us is that those are the eigenvalues. Those are the possible eigenvalues to this eigenvalue equation with this initial condition. Okay. So let us focus on now the other part of the equation. So let us bring back the propagation speed. Because we'd kind of really like to solve this equation now and be a little bit more careful about the units and everything. So I think we can just well, yeah, so what should we do? So we can use the fact that now we know that phi double prime equals lambda n times phi. So I think that if you now just substitute that into the equation, you'll get something like phi double prime phi. This was what, c squared? You'll get v double prime phi minus c squared phi double prime equals 0. Of course, phi double prime is now lambda n times phi. And being an eigenfunction means that you're not identically 0, so I can divide by you. And I'm left with now, I mean, this is the equation we knew we had before, but we're taking into account the eigenvalues and the c squared. So we get v double prime equals c squared times lambda n times v. Right, so the constant has a more special form. You kind of can't have it both ways, right? Like once you've found these eigenvalues, in order to actually solve this equation, like you couldn't have the constant be equal to two different things, right? So now we need to solve this equation with this constant. So this is not an eigenvalue equation. In the sense of you're not solving for like the eigenvalues and the eigenvectors. You're solving for the eigenvectors only. So that's why that one's not called a Helmholtz equation. So this is, so before we were solving for, you want to find k and phi. So this is like a nonlinear equation. This is determined, and now you have like a linear equation for v only. You're not solving for this constant. Yeah. It's the same thing in linear algebra. Like that's why eigenvalues are hard, because you have to kind of solve for that as well as the other two. But this is kind of more mapped out. And yeah, right. So we do make this definition that omega n is square root of lambda n. So I guess you're, excuse me, you're right, Leo, these will turn out to be on the nose, the frequencies. But let's see that. I mean, this is the proof. So let's solve this equation. And I missed a minus sign because it wasn't lambda n, it was negative lambda n. So let's solve this equation. And so let's write down the characteristic polynomial for this ODE. You can write it down straight away, that r squared equals minus c squared lambda n, and therefore r is equal to plus or minus I times c times square root of lambda n, so plus or minus I times c, or plus or minus I times c times omega. Is that how I want to do this? No, I want to put c in with the omega. So sorry, yeah, I take it back, Leo, you weren't. So this is on the nose, the frequency, because you want the right units. You want this to have units of 1 over time, and so you need distance over time over distance. Right? Right. And so with that notation, I can write this as plus or minus I times omega n. And so now my solutions to this ODE equation are really going to be v of t equals some complex number a sub n times e to the I omega n times t plus maybe some constant b sub n times e to the minus I omega n times t. And you'll get one solution for each n. And then this general form for the solution. And you might even call this like V sub n. And that's why we defined omega like we did, because we wanted it to actually be a frequency. So that's what the frequencies should look like. And this now gives us the so-called pure tone solutions, just by multiplying them together, right? All multiplied by, what was it, sine of just square root of lambda n, which is just pi n over L times x. Oh, well, there's no need to add an extraneous constant. And so I think that, but, you know, by linearity, if this is a solution, certainly any scalar times this is also a solution, that's true. So these are the so-called pure tone solutions that model vibration of the string at frequency omega n. And you might be concerned that I'm switching to a complex number here. You might really want a real solution. You are real if you are equal to your own conjugate, and this will be equal to its own conjugate. You can check that out if A sub n conjugate is equal to B sub n. So if you choose your constants to satisfy that relationship, then this will really be a real solution. But other than that, you can choose them freely. Or if you don't mind complex solutions, then choose them arbitrarily. So now we can go back and answer kind of like, what is the fundamental tone? The fundamental tone is omega 1. So the fundamental tone is determined by the length of the string and the propagation speed. And now we can also derive this law. I'm sure I'm going to pronounce this guy's name wrong, this Mersen's law, which says that, you know, relating this to hertz, right? So what is it? Something like 1 over the period is the frequency. So you end up with like omega 1 over 2 pi, just substituting in what things are equal. This is 1 over 2L times square root of T over rho. Remember, C is square root of tension over density. So your book notes that this was sort of first published in 1637, I guess even before D'Alembert's solution. And this is like telling you the frequency in hertz or something like that. Yeah, this is C, square root of T over rho. Yeah. Okay, and so how does this square with the work that we've already done? So the work that we've already done was focused on choosing an initial condition and then, you know, seeing what happens. Here we chose a special form of the solution where the variables are separated. And we found these special solutions at certain frequencies. So you can go back and find the initial conditions now that lead to these solutions. But it's just sort of like a little bit of a different approach. What's the question? Stack the what? Oh, you can look, so, right, you can look at like superpositions. You can start adding these solutions together to get more solutions. There's pictures of these that you can look at. You start to find that at the higher frequencies, you get these pictures that have these nodes, these stationary points. And then that leads you to this musician's trick of, if you place your finger right on the node, you're eliminating frequencies that are kind of lower, because any solution that wasn't constant there gets eliminated when you put your finger there. But you're allowing these higher frequencies to percolate. So that's why you'll see some orchestra violinists lightly touch their finger in just the right place, and they get the overtone out of the string. So it's not exactly, because this is just a model, but that's what's happening. So pretty cool stuff. So say what? Yeah, the comment was you have to be a pretty good musician to do that, and you're totally right. I never played violin, but when I played trumpet, I hung out with a bunch of violinists, and they were always like, it was like, hey, play the violin, And I'm like, no, your instrument costs like $200,000. I don't even want to touch it. But like, just give it a try. And whenever I try to play an overtone, it just it never worked. But so it's not mathematics. Let's be clear. It's not mathematics that it's actually like guiding you how to play the overtones. It's just sort of explaining it after the fact. Well, okay. So what I want to do next time is actually focus on Helmholtz equations that look like this. And so basically, we're going to look at dimension n equals 2 and dimension n equals 3. And here we'll use polar coordinates, and there we'll use spherical coordinates. So get ready next time. Sharpen up your polar coordinate form of the Laplacian and your spherical coordinate form of the Laplacian.